All right. So, as mentioned earlier, we found that I of t is equal to 0.5 e to the power of negative t minus 0.4 t e to the power of negative t. And please check the steps. I might have done some mistakes, but this is a great example to test out on LT spies. Let's say we are not sure, as we did in the TA during TA meeting, we are not sure about this answer. So we're going to simulate the circuit and see if we get the same results. So let's open our LT spies, new simulation, voltage source, uh, capacitor, resistor, where the value of the where the capacitance is 200 micro. I'm sure, I'm sorry, but the dimensions are very small. It might not be clear, but all right, let's just simulate everything quickly. Well, the resistance is 5. The voltage source is, that might be a bit tricky. It's V of S is 2 over S plus 1. And we mentioned V of S is equals to, from part A, 2 exponential e to the power negative t times U of t. But if we pick an exponential node, you'll find it's a bit complicated. So there is this function. So there is this function that defines the relation, so that defines the parameters needed to create an exponential source. We can discuss it later, but for our V initial is 0. Actually, our signal starts with 0. Our pulse is 2. Rise time, our signal is actually falling. Rise time is 0. Rise tau is 0. Fall delay is fall delay is 0. We don't have any delay. Fall tau is negative. Fall tau is negative 1. So this is the most important parameter. Fall tau is fall tau is 1. Yeah, it's not negative 1 because it's 4. Rise tau is 0. We don't have any rise component. V pulse is the amplitude, I think. We can check this function. You can check the function for those parameters. But let's test everything and see. Uh, create wires. Create an initial condition. If we are satisfied with those values, let's create an initial condition dot IC. So we have from our equation, from our notes or our question, we have V of C1 equals 4.5. Let's put it here. And what kind of simulation we're gonna do? Simulate. First, we should place a ground. So if everything is correct, we can simulate configure analysis. Let's do a transient simulation for 5 seconds. Usually it's 5 times tau. Well, tau was 1, so it's usually we simulate for 5 taus. That's when a capacitor is fully charged, or sometimes some people like to go for 10 taus. Everything else can be left as default. Let's put this simulation here and let's run. We might have mistakes that we can correct. So let's first check our source. So is this correct? If we aren't sure and we want to check, we can check it quickly in Matlab. Let's plot or let's create a time t equals 1, step size is 0.1 to 5 seconds, and our source Vs equals 2 times exponential negative 1 u of t. It doesn't really matter. It does matter, but negative 1t. So let's plot. It's great. figure PVS. So yeah, I mean, like they look the same. So it's this. So the output, the input, the source is correct. We can check it in more details. We can pick parameters or pick points and check at them, but they look similar, so our source is correct. What about our output? So our output, we're measuring the current. So let's measure this current. So it looks like this. Let's check it in MATLAB. So we mentioned that our current IC, let's plot IT. Oops, I hope everything is clear. All right, let's plot I underscore T equals, can copy this part, equals 0.5 times exponential e to the power negative t minus 0.4 exponential e times t 0.4 times t times exponential of negative t. Let's create another figure because uh, the scales are different. One of them has a scale of the voltage, like the current has a much smaller scale. So let's plot I of t here. Right here. Multiplying a value, as you can see, our voltage source and our current at the load are correct, or we can check them for the values, but they look similar. So like on a first glance, our results seem to be correct. All right.